All right, this is our area and volume test review. Let's take a look at problem number 1. It says region R is bounded by the graph of y equals negative x cubed plus 8, the x-axis and the y-axis. So let's draw a picture of what this looks like. I'll use this little space right over here. So we've got y-axis, x-axis. Let's see, negative x cubed plus 8. So that's a cubic function, so it's and negative. So it's going to look like this. Okay, it's been shifted up 8 units, so I'm just going to put an 8 up here. Okay, so there's 8. And you can plot point 0, plug in 0, I get out 8. Okay, looks like if I plug in 2, because 2 cubed is 8, I'll get negative 8 plus 8 is 0. So it looks like it's going to cross down here at 2. This is not really, this is kind of skewed, but that's okay. So 8 up here, 2 over here, the x-axis and the y-axis. So we're looking at this region right here. Okay, we want to find the area of that region. So looks like we could do this either with respect to x and do vertical lines, or we could do it with respect to y and do horizontal lines. Since it's already written with respect to x, I'm just going to stick this way and do it like this. So to find the area, it's top minus bottom. So our equation is going to be from 0 to 2, and this is dx. We've got our equation negative x cubed plus 8. So negative x cubed plus 8 minus the bottom, which is 0, so minus 0. And there's our equation. So we just need to type that into our calculator and figure out what we get. I got 12, exactly. That's kind of fun. So 12 units is how big that area is. Okay, let's take a look at part B. So let me scroll over here a little bit so I can see part B. There we go, still see our picture. Okay, so find the volume of the solid generated when this region, R, is rotated around the line y equals negative 2. So y equals negative 2, it's going to be down here someplace, so negative 2. So I'm rotating it around this line right here. Okay, so this region is getting rotated like this. So I want to keep it with respect to x, since we are rotating around a line parallel to the x-axis. So this is still going to be in terms of x. What's happening though is we are creating circles, like so as, for example, as this point right here gets rotated around that and comes back to where it was, that's creating a circle, right? We will have a gap here in the middle, so we need to figure out the volume generated by this outside line first, and that's all the way down to that red line right there, and then we'll figure out the volume generated by the inside line down to the red line and subtract it from the other one. So here we go. So our equation is going to be, we are still stacking these things from 0 to 2. We need to find the volume created by this outside line. This outside line is generating circles, so we are going to be adding areas of circles, so pi r squared, and then we'll minus the area of the circles generated by that line right there, so minus pi r squared. And this is all with respect to x. Okay, so let's see. We this outside one, it's going to be this boundary right here, which is negative x plus 8. Subtract the axis, so negative x plus 8. Subtract our axis of rotation, which is negative 2. And what that does for us, the negative x plus 8 gets us this far, and then the minusing a negative 2, so it's like adding 2, gets us the rest of the way, the rest of that radius all the way down to the axis of rotation. So there's our first circle. Do the same thing over here. This line right here is just 0. And then I want to subtract the axis of rotation, which makes it positive 2, right? That's how far it is right there. And there we go. I just need to throw in another bracket there. There we go. Close that bracket off. Looks good. There's our equation. Now we just have to type it into our calculator. I got a whopping 409.3046. So you can round it up to be 0.305, or you could just leave it like that at 409.304. Okay, let's take a look at part C. The region R is the base of a solid now, okay? For this solid, each cross-section perpendicular to the y-axis is a square. Find the volume of the solid. Okay, so we're no longer, with respect to x, we're no longer drawing little lines like this. Let me redraw this graph just really quick. So we're up here at 8, and then we're out 2, it comes down like so. Okay, so we are now drawing our lines, or these lines represent the distance between the graph and the y-axis now. Those represent the edges of squares. So I'll just highlight one of those lines. So we'll just do like this one right here. So that green line represents the edge of a square. And all those blue lines do too. So if I put some glue here, I'd be gluing it like right on top of that and sticking out of the paper, out of the screen. So let's see. So what we're doing, I want to find this volume. So we were adding up from, these are y values now, 0 to 8, from 0 to 8, the area of these squares. And this time we're doing it with respect to y. So how do I find the area of the square? Well, first I have to find something that will represent this side length right here. So it's this equation right here minus this equation right here. Well, this one's 0, that's easy. This one right here is negative x, this negative x cubed plus 8. So what we need to do is we need to get x by itself. It has to be in terms of y. Everything in this equation needs to be in terms of y. So this equation right here, I'm going to write my work over here. So I have y equals negative x cubed plus 8. Let's get the x by itself. So I'm going to subtract 8. So y minus 8 equals negative x cubed. Multiply everything by a negative. So I get negative y plus 8 equals x cubed. And then I'll take the cubic root of both sides, or it's the same thing as raising both sides to the 1/3 power. Okay, I don't need to consider plus or minus because it's a cubic root, it's an odd root that doesn't include plus or minuses, it's only with the even ones that it does. So there's my equation. So that will give me the distance because this is the top guy right here, and minus 0, that will give me that distance right here. So this right here will do it for me. So I've got negative y plus 8 to the 1/3 power. Well, to find the area of a square, all of the sides are going to be the same thing, so I just have to square this or multiply it by itself. So I've got negative y plus 8 to the 1/3 power. So when I take negative y plus 8 to the 1/3 power and I square it, just to make my life a little bit easier when I type this in my calculator, I multiply those two numbers together. This is going to be 2/3. So 2/3. Okay, so that's the area of my squares. I'm adding them up from 0 to 8, and to get the total volume, since this right here basically represents the area of those squares, and this right here represents the depth, but that's the depth as it gets closer and closer and closer to 0. So these are very, 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 very thin crackers. With their saltine crackers, that's what they kind of remind me of, squares, right? Anyways, and I'm stacking them all up, and I'm finding the volume of these little guys and adding them all up. Anyways, so let's see. We type that into our calculator, and what do we get? At 19.2. Lots of zeros and a 37. So I kind of wonder if my calculator got 0.000037. I kind of wonder if the actual answer is 19.2 exactly. Since we're dealing with a cubic root, calculators are kind of funny. Anyways, I wonder if it's a little bit extra stuff. Might not be, I don't know. So anyways, but this will be good enough because I just went out 3 decimal places. 19.200 is the correct answer for C. All right, so let's take a look at question number 2, part A. All right, so region R is bounded by the graphs of x equals y squared minus 4y plus 8, x equals negative y squared plus 4y minus 2, y equals 0, and y equals 4. So I'm going to graph this one. I'm lazy. I'm going to graph it on Desmos. You could just plot points if you wanted to. I'm just going to graph it on Desmos. So here's what a graph of it looks like. All right, so that's what it looks like. And let's see. This equation right here, this blue one is actually this guy right here. This red one is that guy right there, and the orange one is y equals 4, and then that green one there on the bottom is y equals 0. So that's our graph right there. All right, so let's take a look at what we're doing here. Part A, we're finding the area of region R. Now, it would be a mess to try to find the area using vertical lines like that. It would be ugly. with respect to x. It just would. I'd have to find the equation for this thing. I guess it would be identical. I could cut it here in half and find the area that way. But I'd have to do 3 different integrals because the bottom bound would be changing 3 times. So it would just be a nightmare doing it that way. So, but if you look at it with respect to y, it's actually pretty easy. So I've got, if I'm going this direction now, and I cannot draw horizontal lines very well, if I'm going this way, my top equation, it's bounding these on top, is the same as it is on the bottom. I mean, it's the same the entire time. The bottom one is also the same the entire time. So let's do it with respect to y. So we're going to write our equation. We are stacking these things from 0 to 4. And our equation is going to be top minus bottom. That's with respect to y. So our top is y squared minus 4y plus 8 minus the bottom, which is negative y squared plus 4y minus 2. And there's our equation. Now we just have to type in your calculator. You can clean this up a little bit if you wanted to. I mean, you could distribute that negative. It looks like we'd end up getting this. You got to be careful because you don't want to accidentally get the wrong answer just because you simplified wrong. But if I distribute that negative, it looks like I'm going to end up getting 2y squareds. This negative will make that a negative 4, so I'll get negative 8y. And I'll have positive 8 plus 2, so plus 10. Might be a little bit easier to type in your calculator like that. But let's type it in our calculator and see what we get. I got 18.6666, so 18.666 or 18.667. Either of those answers would be just fine. All right, let's take a look at part B. So come over here. Find the volume of the solid generated when region R is rotated around the line x equals negative 4. So let's come back over to our graph. Negative 4 is right here. So I'm rotating this region right here around that axis. Cool. We're still going to be doing it with respect to y. All right, so what's happening here is we're taking, as this line right here gets rotated around that axis, okay, this distance from there to that red line, so all the way up and down, gets rotated around, we get this nice solid shape. But then what we want to do is, as the blue line gets rotated around, it creates this dead space. So we want to subtract the volume generated by the blue line from the volume generated from this red line. So, well, we are doing this with respect to y. So this red line gets rotated. Well, let's do bounds first. Still bounding. It's still being stacked from 0 to 4. Okay. Let's see, this red line right here, as it gets rotated around, just pick a point on here anywhere. Imagine as that point gets rotated around that dotted line, okay, it's going to create a circle. So we're adding up areas of circles. That's what we do all the time when we rotate. So it's pi radius squared. And then the blue one, as it gets rotated around, I'm going to subtract the volume created by that one. So minus pi r squared. And this is with respect to y. So the red line is y squared minus 4y plus 8, and that will get me to the y-axis. So that will get me that far right there, or that far on that green line. I need this extra space right here because I need my radius to be the whole thing. So we're going to subtract the axis of rotation. Axis of rotation is negative 4. And you'll notice by minusing a negative, it's going to end up adding 4 more onto that line, which gets me the distance I need. Okay. So there you have it. There's the first one. I got parentheses a little bit bigger. The bottom one, same thing. So negative y squared plus 4y minus 2. Subtract the axis of rotation, which is negative 4. And there's our equation for finding the volume of this shape. Now we just have to type it into our calculators. And we got a pretty big number, 821.0028. So 0.002 or 0.003, either one would work just fine. All right, let's take a look at part C. So the region R is the base of a solid. For this solid, each cross-section perpendicular to the y-axis is a semicircle. with diameter in R. So I'm going to come up here a little bit. I'm going to erase some of this business going on up. Oh, darn it. I drew on the graph itself. Okay, I'm not going to draw on the graph. Oh, I can fix this. Watch this. Paste a new picture on there. Ha, cheat. Okay. There we go. So there's our picture again. For this solid, each cross-section perpendicular to the y, so we're still dealing with lines perpendicular to the y-axis. Okay. They are semicircles, so let's highlight one of those lines that I just drew. We'll just pick one at random. It could be anywhere, it doesn't matter. It's just to kind of give you an idea what's going on. So I'm going to do that one right there. So that line represents, let me come over here, draw that same length-ish, the diameter of a semicircle. Okay, so this green line is right there on that line right there sticking up out of the page. And what we're doing is we're adding these semicircles up from, looks like 0 to 4. So we were going to take the integral from 0 to 4. We need to find the area of our semicircle, and that's it. So this is with respect to y. So the question is, how do I find the area of a semicircle? Well, to find the area of a circle is pi r squared. So a semicircle will just be half of that. The question is, what is the radius? So the radius itself is going to be half of that green line, right? So this green line is, it's the top, subtract bottom. Okay, and we've done that already. It's up here with top minus bottom. In fact, we even simplified it. That's nice. So this right here will give me the distance between the red and the blue lines. Okay, so this whole entire green line is 2y squared minus 8y plus 10. And I want half of that because that's my radius. So the area of my semicircles is pi radius squared everything divided by 2. Okay, so my radius is, we could do 2y squared minus 8y plus 10 cut in half. And there's my equation. And you can simplify that down a little bit if you want. I don't want to get too carried away, but it might be easier to type in your calculator, at least if you do this division problem up here. So the 2's cancel out. So you'd have y squared minus 4y plus 5. That's as much as I would do. I wouldn't try squaring it or anything. But anyways, go ahead and type that in your calculator. Let's see what we get. 43.1445. So you could round it up, or you could just leave it as it is. 0.144 or 0.145 would be the volume of that solid. All right, let's look at problem number 3. It says region R is bounded by the graphs of y equals 2x and y equals the square root of 5 minus x and y equals 0. Let's do this one by hand. We'll graph this guy by hand. So let's see, we've got, let's draw some axes here. Okay, let me make my pen size a smidge bigger. All right, so let's see, we've got y equals 2x. Let's get some lines in here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3, 4. Okay, so y equals 2x. That's a linear equation. It's y equals 2x plus 0. So it crosses. Let's do it. Let's do this. Let's do different colors here. We'll do blue for this equation right here. So we'll do this one in blue. So y equals, so it crosses through 0. Slope is up 2 over 1. So 2 over 1, 2 over 1. That's pretty good. And then we've got that line right there. Okay. Let's take a look at this one right here. Do this one in green. Square root of 5 minus x. Let's see, if I want this thing to go to 0, I need my x value to be 5, because 5 minus 5 is 0, square root of 0 is 0. So if I plug in 5 for x, I get out a value of 0. 1, 2, 3, 4, 5. So I know it's right there. If I plug anything bigger than 5 in, I'm going to get a negative number, so that's not going to work. So let's plug in another nice friendly number. Let's see, square root. Next one will be square root of 1, which will be nice. So if x could be 4, 5 minus 4 is 1. So I plug in 4, I get out 1. Next friendly square root would be, if I can get it to be 4. So if x were 1, I would get out an answer of, so if x were 1, 5 minus 4, 1 is 4, square root of 4 is 2. So it looks like they're going to intersect right there. So my graph looks something like that. Okay, I can't get any negative y values because it's a square root. So I'm looking at this region right here, it looks like. Okay. So let's see, find the region of R. Okay, so we have a couple of options here. We could do it with respect to x, like so. Which I think I'm going to do it this way just because I'm lazy and I don't want to switch my equations around. But look at the downside to this. This region over here is bounded on top by my blue line, and then at that point it switches to be bounded on top by my green line. So I'm going to have to do two different equations. If I did it with respect to y, so let me show you what that would look like. So let's erase those lines. If I did it with respect to y, that means that I'd be doing it this way, and you'll notice that these lines are always bounded on top by the green line, always bounded on the bottom by the blue line. So I don't only have to do one integral, but I would have to switch these around so x's are by themselves, which isn't a big issue, but you can do it either way and get the same answer either way. Since they're already written in terms of x, and it's probably the same amount of work either way, I'm just going to do it. I'm going to do two different integrals. Okay, so our first integral, we are going from 0, they're being stacked from 0 to 1, x value of 1. Okay, we're doing top minus bottom to figure out the area. So my top equation is the blue line, so 2x. Well, that's a lot more room than I'm going to need. 2x, and the bottom line is 0, so 2x minus 0. Okay, that right there will give me that the area of that triangle right there, so that guy right there. Okay, and then I want to add to it the area starting at 1 and going to 5 of my green line on top. So square root of 5 minus x minus the bottom, which is minus 0. And let's see, I need to make, so I've got, this is dx, I've got to make sure that dx is multiplied to everything. So I'll put a parenthesis there, and it looks like a parenthesis, whoops, Control Z, I already got a dx over there. Oh, I'm okay, I'm just fine. I was thinking that dx needed to be for the whole thing, but it doesn't. I forgot, I'm doing two different integrals. So I'm good. I've already got a set of parentheses around this right here. Alright, so now we'll just type that into our calculator, so we get. Alright, for this first integral, I got just 1, which makes sense. I mean, look, it's a triangle, right? So the rectangle itself would be height of 2, width of 1. So that's 2, cut that in half is 1. That makes perfect sense. And then this guy over here, this region over here, I've got 5.3333. So our final answer will be 6.333. And there's our area of region R. Okay, let's take a look at part B. So we've got the region R is the base of a solid. For this solid, each cross-section perpendicular to the y-axis is a rectangle with base in R and height equal to twice the base. Find the volume of the solid. Okay. Well, let's see. So first things first. We are no longer with respect to x, so I'm going to come back through here. I'm going to erase the stuff that we did on that last problem, last part. Get rid of those. We are now going with respect to y, so like so. Okay. Let's see. So each of these cross sections, so we'll highlight one of them. That is a rectangle. And that's the base. The base is in R, that region. So that's our rectangle. Okay, and it says the height is equal to twice of that. So these are something like that. It's more like a hat, but that's okay. So this is our rectangle. Okay. So what we need to do is find the volume of this solid. So we are stacking these things from 0 to 2. Area of our rectangles, dy. Okay, to find this distance right here, I need to take top minus bottom. But keep in mind, we're now dealing with y with respect to y. So I need to get the x's by themselves. I need to put it in terms of y. So let's change the green one first. So I've got y equals, let's do this in green. Why not, right? Because we can. Y equals the square root of 5 minus x. So I'm going to square both sides. That gives me y squared equals 5 minus x, subtract 5, and multiply by negative, so it becomes negative y squared plus 5 is equal to x. So that's this equation right here in terms of y now. Okay, and then the blue one, it was y equals 2x, and now just divide both sides by 2, and that's the equation for this line right here. So we're finding this distance right here. So this red distance right here, it's the same as that. It's simply just this equation, negative y squared plus 5, minus this equation, so minus y over 2. So this right here, that's our distance right there. So to find and then that means that this distance right here, so that length right there is just twice of that, so 2 times negative y squared plus 5 minus, I'm going to put 1/2 y. It's the same thing as y over 2. Right there. So there's that. We want to find the area of this rectangle, so it's this equation, or sorry, that expression times that expression. So I've got, in fact, since this and this are the same thing, what I really have is 2 times negative y squared plus 5 minus 1/2 y squared. And that's what I type in my calculator. That will find me the volume of the solid generated by these rectangles. I got a nice 48.8 for that solid volume of that solid. Okay, let's take a look at part C. All right, it says, this one's different. It says the vertical line x equals k divides this region R into 2 regions with equal areas. Write but do not solve an equation involving integral expressions whose solution gives the value of k. All right, so let's see what's going on here. I'm going to come back up here and I'm going to use this picture again. So, however, let's see, x equals k, so that's going to be a vertical line. So I want to get rid of this, all that stuff from part B. All right, somewhere in here, there is some vertical line, x equals k. I don't know where it's at, but it splits this, 6.333, right in half. So it's probably, I don't know, it's probably someplace in here-ish. Okay, I'm just going to kind of put a little line right there. That's x equals k. All right. So what I want to do is I want to come up with an integral expression, so an expression involving integrals, where if I were to solve it, which we've never really learned how to do, okay, we've never learned how to solve for k in this sense, because you'll see where k is at. It's going to be in a bound, okay. But if I were able to solve it, I could figure out what k is. So let's see what's happening here. I've got this area over here, okay. This area over here is the same size as this area over here. So there's a couple of ways of doing this. First thing I know is this area over here is a little bit trickier because, well, it's not that tricky. I guess it's just because the top part is, changes. But let's look at this 2 different ways. There's actually 3 ways of doing. 2 of them are essentially the same, and one of them's different. One thing I can do, I could say, hey, this area right here, from 0 to k, and I'd have to split it up into 2 integrals, okay, equals half of that number. That's option 1, okay? So I'm going to say option 1, all right, is saying this guy right here is equal to half of that. So let's just do that really quick. Remember, you only have to do one of these, but whichever one makes the most sense. So let's talk about that. So that's the integral from 0 to 1 of top minus bottom. So this is 2x minus 0, okay? Plus the integral from 1 to wherever k is at. I don't know where k is at. I just know it's going to be on that side of 1. 1 to k. It would be a really issue if we weren't sure that k was on the right side of this triangle. But since this is 5.333 over here, the middle of this shape is definitely on the right side of that triangle. Anyway, so we got square root of 5 minus x dx. So that value right there, so that's finding the volume of this shape right here, has to be equal to 6.333 cut in half. Okay, there's option 1, and that would be full credit right there, perfect. Okay, option 2, is very, very similar, except for instead of taking this side over here, I'm taking this side over here. Okay, so this is option 2. Sorry, it's really hard to see that yellow. Option, oops, not optional, option 2. Option 2 is going from K, so I'm starting at K, and I'm going to 5, and I'm saying that the area generated by this curve, square root of 5 minus x minus 0, right, dx, is equal to half of the value, 6.333 over 2. So that's option 2, okay? The other option is to say, hey, this region right here has to be identical to the area of this region right here. So it's basically saying taking this piece right here and setting it equal to this piece right here is essentially what it is. So let me write that out. Option 3 is saying, hey, if I take the area of the first part, so from 0 to 1, 2x dx plus 1 to wherever k is, square root of 5 minus x dx. That has to be equal to, so that's the area of this region right here, okay? That area has to be equal to this area. And this area right here is generated from k to 5 and square root of 5 minus x dx. Either one of, any of those three options, any one of those would have worked just fine, okay? And it says write but do not solve. So all I had to do was write it. So that's full credit right there just for writing one of those three equations. All right, let's take a look at problem number 4. Okay, problem number 4. Region R is bounded by the graph of y equals 2 sine of x and y equals negative cosine of x minus 1 between 0 and pi. So let's see what this looks like. If I had a graph, so here we go. Doing trig functions, let's count by pi halves because that's nice. So that's pi halves, there's pi, there's negative pi halves, there's negative pi. And it looks like we're multiplying the sign by 2, so that's going to expand how high it is. So I'm going to come up here to 2. So there's positive 2, we'll go down to negative 2. All right, so let's take a look at this guy right here. Y equals 2 sine of x. So basically it's taking sine of x and it's stretching it vertically. So we've got sine of x does cross here. When I plug in pi halves, I get out 1, which means I'm going to take that answer and multiply it by 2. So instead of getting out 1, I'm going to get out 2. Plug in pi and I get out 0. 0 multiplied by 2 is still 0. Then we're going from, that's enough for this because we're just going to 0 pi, but just for fun, we'll graph over here. Negative pi halves, and plug that in, I get out negative 1 when I plug it into sine, times 2 is negative 2, and pi. So there is our graph, oh that's really bad, graph of sine. Now it's graph y equals negative cosine x minus 1. So if I plug 0 in for cosine x, I get out a positive 1. So that becomes negative 1. Negative 1 minus 1 is negative 2. So we're right there. Let's plug in pi halves. Cosine of pi halves is 0. So minus 1 is negative 1. And plug in pi. Cosine of pi is negative 1. So negative 1 plus times the negative is positive 1. Minus 1 is 0. All right. Just for fun, let's go over here to negative pi halves. Negative pi halves of cosine. That will also get us 0. So this could be negative 1. And you see the pattern, negative pi is going to make that equal to 0 as well. Okay, so this is what our function looks like. Okay, and we are just going between 0 and pi. All right, so find the area of region R. So let's see, we're taking, looks like, and we're just going from, it looks like from 0. So from there to there, okay? So we're doing little vertical lines like that. So we're doing this with respect to x. So let's see, we've got the integral starting at 0 and going to pi of top minus bottom, and with respect to x. So it looks like our top is 2 sine of x minus the bottom, let's put this in parentheses, minus cosine of x minus 1. And there we go. Type that into our calculator and we'll get our area. I got 7.1415. So 7.141 or 7.142. Either one would work. Okay, let's look at part B. All right, the region R is the base of a solid. Okay, so this is the base of a solid. For this solid, each cross-section perpendicular to the x-axis, so just as we have it drawn, is a circle with diameter in R. Find the volume of the solid. All right, so let me highlight one of these cross-sections. So all these cross-sections right here represent the diameter of a circle. So let me just pick one random. I'll just do, let's do this one right here. So that guy right there. That is, let me draw a picture over here. Let's put it right there. The diameter of a circle. Not bad. All right, so we are stacking these circles, so it's kind of going through the screen and out of the screen, so through the paper, out of the paper. It's kind of fun. So we need to add up these circles from 0 to pi. We're going to have the area of these circles with respect to x. So let's see, how do we find the area of a circle? It's pi times the radius squared. All right, so this is the diameter. So how do we get that? That's going to be the top equation, red, minus the blue equation. Okay, that will give me that distance right there. So let's see, this length, that green length, is 2 sine of x minus a negative cosine of x minus 1, which you can clean that up to be 2 sine of x plus, in fact, I'm going to do that, 2 sine of x plus the cosine of x plus 1. So that's this length right here, but I need the radius, so I need half of that. So that right there is going to be my radius. So up here we've got area of our circles, our pi, the radius squared. The radius is 2 sine of x plus cosine of x plus 1, all cut in half. And that will give me the volume of my shape. And we get 14.9190. So 14.919. Okay, last question. Part C. Here we go. The value of K divides the solid in part B into two solids of equal volume. Write but do not solve an equation involving integral expressions whose solution gives the value of K. All right, so I remember so part B, our volume was generated by cross sections perpendicular to X, where the cross sections, like this green line right here, represent the diameter of a circle. So what we got going on here now is, let me come through. Can I erase? Was I smart? Oh, good, I was smart. Sometimes I don't put them on different layers. So let me erase this, just kind of clean it up a little bit. So I'm still going from 0 to pi. So I still have these lines right here, okay? But what I'm trying to figure out now is someplace in here, I don't know where, so I'm just going to kind of split it kind of in the middle, but I don't know if that's exactly where it's at, okay? So somewhere in here is some value of K, all right, where the volume generated on this side by those cross sections and the volume generated on this side by those cross sections are exactly the same thing. Okay, if you've already done problem number 3, part C, you'll see that there are 3 different ways of looking at this, and just choose whichever one makes the most sense to you. Okay, so let me show you. Option 1 and option 2 are basically the same thing. Option 1 is saying, hey, if I find just the volume of this piece using those cross sections, okay, it should be half of my answer from part B. Okay, so for example, so option 1, I guess option 1, it's saying, hey, if I find the volume of this first piece, so I'm going from 0 to K, wherever the heck K is, I don't know where it's at, but it was from 0 to K, and the volume generated by that, so it's going to be the same equation I used over here, that ugly thing, pi 2 sine of x plus cosine of x plus 1 divided by 2 squared, right? If I find the volume of that, it should be equal to half of this number. So 14.919 divided by 2. Or you could just type in this, you could write this whole thing and just put a 1/2 out in front of it. That would work too. Okay. Option 2 is very, very similar. It's just taking this side over here and saying it's equal to half of that number. So all that's going to change from option 1 to option 2. So I'm going to put option 2 right next to this because it's basically the same thing. The only thing that changes are the bounds. Now I'm going from, instead of from 0 to k as I would with option 1, so option 1 is from 0 to k. Option 2 is from k to pi. And boom, everything else is the same. Okay. The other way, or once again, you could rewrite this to be this entire equation over here with a 1/2 out in front of it, or divided by 2. Either way works. Finally, the other way of thinking about it is, well, what if, let's see, let's get a different color here. What you could do is find the volume of this piece equals the volume of that piece. So we've got, so this is option 3. I just changed my putrid color. Option 3 would be this first piece, that green piece. So 0 to k, and then we'd have all this gibberish right here. So pi 2 sine of x plus cosine of x plus 1 over 2 squared. Oops, sorry, I forgot a dx in there. Dx, that piece equals the other piece, which would be the same thing but with those bounds. So from k to pi of pi 2 sine of x plus cosine of x plus 1 over 2 squared dx. That would be just fine as well. Okay, any one of those options, it all gives you the same answer. All right, and that takes care of our review.